Okay, so we were doing problems on chapter 3. In problem 3, in the following figure, the fluid is gasoline where the density is 680 kilogram per meter cube at 20 degrees at a weight flux of 120 Newton per second. Assuming no losses, estimate the gauge pressure at section 1. So what we have here, they gave us a fluid flow. We know the weight flux. What do we mean by the weight flux? Who will tell me how we can get, you know that the weight is m times g, okay? So the weight flux is m dot times g. So if I want to write here, just 1 minute because people are still entering the meeting. So when they tell you a weight flux, the unit is a Newton per second, okay? And it's equal to m dot, which is the mass flow rate, which is in kilogram per second, times g, okay? Because you know that W is m times g, so W dot is m dot times g. So if you want to get m dot, you simply say m dot is equal to the weight flux over g. And if you are interested in q dot, okay, which is so this is m dot is the mass flow rate. It's the mass flow rate. Okay, if you want the volumetric flow rate q dot will be equal to the weight flux over gamma, okay, which is equal to m dot over rho, okay. And in this case, the unit of the flow rate, the volumetric flow rate, will be meter cube per second, okay. And this is called the volumetric flow rate, okay. Here we are interested, why we are interested in the volumetric flow rate? Because we need to find the velocity, okay. Since here we want to find what is the gauge pressure at section 1. And whenever you have a flow, yes, whenever you have a flow between two locations, and all conditions for Bernoulli equations are here because we have steady flow, incompressible. We can neglect viscous effect because we are considering here, if you want to have the flow in the circular tube, you will take a streamline that is far from the walls. So if you take a streamline like this, which is at the middle, at the center, you can apply Bernoulli between, if you want, the inlet and the exhaust, okay? You have the inlet section is here. So you are interested mainly at this location. At this location, you need to find what is the gauge pressure at 1. So P1 is not known, okay? P1 is not known. And I want to find what is V1. To find V1, I can correlate with the volumetric flow rate because they gave me the weight flux. And from the weight flux, I calculated the volumetric flow rate, which is in meter cube per second. So I can get V1 because V1 is equal to the volumetric flow rate over A1, over the cross-sectional area, okay? So here I can calculate it. It's equal to a Q, which is 120 over gamma of my fluid, which is rho times G. So I have rho, which is 680 times G, which is 9.81, okay? So I know the value of Q. Now what about A1? They gave me, I have a circular cross-section of diameter 8 centimeters. So I
دكتور
can...
بس كيف كيو 120 مش هو الويت فلكس 120؟
ايه بس ما انا عملت I divided over what? I divided over gamma, okay?
Okay.
Because we said that Q dot is weight flux over gamma, okay? Then I should multiply, then I should divide my result. I should divide my result by A1. Now what is A1? A1 is equal to pi times d square over 4, okay? And I have the diameter equal to 8 centimeter. I should not forget to convert to meter. So it's equal to pi times 0.08 square over 4, okay? From this equation now I can compute the value of V1. Now, for section 2, what do I know about section 2 at the exit? At the exit level at section 2, it's a jet open to the atmosphere. Because the jet is open to the atmosphere, you can say that P2 is equal to P atmospheric. And since they want P1 in gauge pressure, so also P2 should be expressed in gauge pressure. So it's equal to 0 gauge. Okay? Now, you can apply Bernoulli between sections 1 and 2. So applying Bernoulli equation, you can say that P1 plus rho V1 squared over 2 plus rho G Z1, okay, equals to. Now what about Z1 and Z2? In order to determine Z1 and Z2, you should consider a certain origin or a Z-axis. You can take the origin wherever you want, because the
Can I take it passing through the...
Yes, the position of the axis will not affect your result, because what you are interested in is delta Z and not Z itself, okay? So you can take here, for example, the easiest reference to take is to consider that at this level, I have, this is Z axis, so this is the level corresponding to 0. Then if Z1 is 0, Z2 will be equal to 12, because as you can see here, this point is elevated from the center line of the first center line of section 1 is at a distance of the second center line with a distance of 12 centimeter. Okay, so I can just replace 0 and 12. So let me make sure that it is, yeah, no, it's 12 meters, sorry, not centimeter. Okay, 12 meters. So the distance, so this figure is not to scale. Okay, so you have here a distance of 12 meters. So I can replace Z1 by, so Z1 is equal to 0 and Z2 is equal to 12 meter. Okay, so now I still have to specify what is V2, because I already have found everything. Still I need to find V2. For V2, from continuity equation, okay, you have that Q1 equal to Q2. So you can say that V2 is also equal to Q over A2, since Q1 equal to Q2 due to continuity, because you have from continuity of an incompressible flow. Okay, continuity equation for, because you know the continuity equation will state what? It will state that the mass flow rate is the same. Okay, but when you have incompressible flow, rho is constant, so Q is also constant. So, and you can see here that at the open jet, you have a diameter of 5 centimeters. So you can calculate the area too. Okay, so A2 is simply, you have 5 centimeter diameter of the opening jet. So you have A2 equals to pi times 0.05 square over 4. Okay, and now you have everything known, unless you have the only unknown is P1, you can calculate P1. And since you replace P2 by 0, so P1 you obtain will be in gauge pressure. Any question for this part?
Yes,
May you
doctor.
repeat just the last thing you did?
Yes. Okay. The continuity, you mean?
Yeah, the thing after continuity.
Okay. The thing after continuity is to replace in this equation in Bernoulli. When you replace in Bernoulli equation, you know all your terms except P1. Okay? We replaced V1 by its value, Z1 by 0, Z2 by 12. Now, for V2 and V1, they are calculated from the flux because you do Q over A. So since P2 is a 0 gauge, when you replace in this equation, you will get P1 and gauge pressure. If you replace P2 by P atmospheric equal to 101 point, you replace by the atmospherical value, which is nearly 101,000 Pascal. If you replace, you will get P1 in absolute. But since they told you find P1 in gauge pressure, you will replace P2 by 0 because P2 equal to P atmospheric, which correspond to 0 gauge, and you will get P1 then in gauge pressure. Okay. This was your question?
Yes, doctor.
Okay. Now,
دكتور
yes.
بس لما عملت انه V1 equal Q over A1
Yes.
شو حطيت الكيو؟ انت حطيتيها كيو دوت هيدا مش كيو عاديه.
Yes, ما هي Q dot. I mean by Q dot. Okay. Look, you have when I say A times V, this is what? This is a volumetric flow rate. In general, we put it Q, but it's a rate. Okay. It's a rate which is in meter cube. This is why I call it Q dot because it's a rate. Okay. In general, they use a symbol Q for the volumetric flow rate. So it's meter cube per second. Okay. And Q is equal to the weight flux WF or W dot if you want over gamma. So once you find the Q, since you have constant flow rate, okay, you can say that Q is the same everywhere. So A1 V1 is equal to A2 V2. Okay.
Okay.
Any other question? Okay, another problem. If losses are neglected in the figure, for what water level H will the flow begin to form vapor cavities at the throat of the nozzle? So here, when we talk about vapor cavities, what phenomena we have?
Cavitation.
Very good. We have cavitation. Okay, and you know that cavitation will start to occur for which pressure?
When pressure equal to
Vapor
vapor pressure.
When we reach vapor pressure. Okay. Now we should not go below this pressure. Okay. So you should, in this problem, when they ask you about cavitation, you should try to look what is the critical location in your problem. At which point I have the lower pressure. So here, if I look, okay, very good. Why at 1?
Because the surface area is less than, so the velocity will increase, and when velocity increases, thus the pressure will drop.
Very good. So first, here, if I compare first between this level and this one, okay, I have here, I can find what is the corresponding pressure at this location, because here I have, if you want, I have until here I have the hydrostatic effect. Then when I go inside my tube, I have a certain velocity. Okay, so if you want here, I can apply Bernoulli between two locations. I can apply it between 1 and 2. And also I can apply it between 2 and this level. I will see why I need to do that. Okay, so let us say the critical pressure, as you said, is here Because if I compare 1 and 2, if I compare these two sections here, okay, because here the velocity is higher, so we know that V1 is larger than V2, since the cross-sectional area A1 is smaller than A2, okay? And we know from continuity, we have that A1 V1 equals to A2 V2. So we can say that in our duct, the critical location is 1, because here we will have, if you want, the highest pressure, okay? So the pressure at P1, so the pressure is minimal at P1. So the pressure is minimal at location 1. This is why we should avoid to reach the vapor pressure at this location. Okay. Now, how to get the expression of this pressure? First, I know that this jet between 1 and 2 is open to the atmosphere. Okay, so I know that the pressure here is PA. Okay, I know that the pressure here is PA. But I don't know what is the exit velocity, so I don't know V2. Okay. Now, concerning section 1, I have several unknowns. I don't know the pressure, so P1 is unknown, and V1 is unknown. Okay. So if you want here, I have 3 unknowns: P1, V1, and V2. Okay. Now, from the continuity equation, I can relate V1 and V2, but I still have as unknown P1 and V1. Okay, so it's not enough for me to write one equation. Can you tell me what should I do to get a second relation?
We begin from the surface, from
yes,
the top.
Very good. We can apply Bernoulli from the surface, between the surface and point 2, because if I want to draw my streamline, if I follow it, it's starting from here, then if you want, it's going, then it's like a curve if you want. So it is like this, and then it's doing a small turn, a 90 degrees turn to go out. So I can also, this is one streamline. So I can apply Bernoulli between 1 and 2, but also I can apply Bernoulli between the surface and the exit jet. Okay, so let us now write all the equations we know to find our unknowns. First, we will start by relating V1 and V2. So as we said, from continuity, we have that A1 V1 is equal to A2 V2. And the diameters are given at section 1 and section 2. So if you want, we can write that V1 is equal to V2 times the ratio of diameters, so times D2 over D1 square. Okay, because if you simplify pi over 4, you will get at the end that V1 is V2 times D2 over D1 square. Now, we have related the velocities. The second step, we apply Bernoulli between sections 1 and 2. Between 1 and 2. Okay, now since 1 and 2 are at the same level, so we don't have, so Z1 is equal to Z2. Let us take Z, this is the origin if you want for Z axis, let's consider. So this is, at this level Z is 0. So
دكتور يعني هيدي equation 1 اللي عملناها هلا equation 2 من Bernoulli.
Yes, the continuity equation is equation 1. Now, Bernoulli equation between 1 and 2 is our second equation. What do we get here? We got that P1, okay, plus rho times V1 square over 2. Okay. Now, since we considered that z on 1 and 2 are the same, so they will be simplified. Okay, so no need to put the hydrostatic term. Equals to P2 is up into the atmosphere. So if you want to work in here, let us work in absolute pressure. You know why? Because in the tables they gave you, the vapor pressure is given not in gauge, in absolute. Okay, so I want to find the value of P1 in absolute pressure. Or if you want, you can find it first gauge, then you can add the atmospheric pressure. So it's up to you. So I have at 2, it's PA plus rho times V1. Now, if you want, you can directly replace V2 by its expression of V1. Okay, to have only one unknown in this equation. Or if it's up to you, you can write V1 function of V2 or V2 function of V1. It's similar. Okay, so if you decided to keep V1 as the unknown, then you will replace V2 by V1 times and of course I want it square, so V1 square, okay, times the ratio, which is now D1 over D2, so times
دكتور
D1.
يعني هون هي بلس رو في 2 بعدين نعملها substitution
Yes,
صح؟
صح. هي rho V2 square over 2, and if I do substitution of V2 square, it's V1 square times D1 over D2. Since D1 over D2 is already to the power 2, and I'm doing square again, so it will be to the power 4. Okay, so what I did is just replacing V2 by its value. Instead of rho V2 square over 2, I have rho V1 square times D1 over D2 to the power 4 over 2. Okay, and plus rho G Z2, but as we said, Z2 is 0, so and Z1 is equal to Z2. So wherever you take your axis, even if it's not 0, no problem. Z1 equals Z2 will cancel out. Okay, so from this equation, this is equation number 2, but still I have two unknowns, P1 and V1.
Doctor,
Yes,
why P2 equal to PA?
P2 because at 2 you have an exit jet, and your exit jet is open to the atmosphere. Whenever you have an open jet to the atmosphere, the pressure at the exit will be equal to the atmospherical pressure.
هون بأتموسفيريك 100.
Yes, 101 times. You can take the approximation إنه هي 101 kilopascal.
Okay, thank you.
Or 101,000 pascal. Okay. So this is equation 2, but I still need, as we said, a third equation because I have 3 unknowns. Now, in order to get the expression of V1 or V2, what I can do is now, as we said, we apply Bernoulli between A and 2. Okay. So if I apply now Bernoulli between A and 2, what do I get? First, at the surface level, do I have a velocity?
No, it's negligible.
No.
Actually, I have a velocity, but I can neglect it. Why we say this? Because you know,
it
for
has a
the
large surface
reservoir,
area.
yes, for your reservoirs, the area, the cross-sectional area is very large. So it is very large compared to A1 and A2. This is why you can say that nearly, approximately V is 0. Okay, because you can write the following equation: V at surface times A surface equals to V2 A2, but A surface is much higher than A2, so V surface is much lower than V2, and we can say so we can neglect it compared to V2. Okay, so nearly 0, we can't neglect.
دكتور يعني يا بنعمل برنولي between 1 and 2 يا برنولي between A and 2.
No, we should do both. Why you should do both? Because look, when you wrote these two equations, how many unknowns do you have?
مع ال H.
You have 3 unknowns, V1, V2, and P1. And if you have 3 unknowns, it's not enough to write two equations. You need 3 equations to solve for P1. Okay? This is why in this problem, it's not enough to write Bernoulli 1 time. We should write it 2 times. Okay? So now, what we will do is we will write Bernoulli between A and 2. Okay? And we say that between A and 2, what do we have? Do you hear me?